coming. This is an excellent turnout. Fantastic. Thanks for coming. We are right in the middle of, I think, a very strong schedule for our seminar series. So keep it coming, and keep it coming to this room right at this time, and we'll continue to provide excellent speakers like we have today. From Cal State University East Bay, Jean Moran is just the new chair of the department there. And before that, she actually was a postdoc at Texas A&M at Texas. And if we go backward in time, also went to Rochester in New York, and was in the Peace Corps in Fiji after her undergrad in Rochester. She's worked extensively lately in the chemistry of groundwaters and nitrates and age dating water and groundwater. So she's very active in research. She's actually taken on some of our undergrads as a graduate student. So we're very lucky and happy to have Jean here to talk about the Northern Sac Valley. So thank you very much.
Thanks a lot, and thanks so much for inviting me. Thanks, Todd contacted me, and I was happy to come out here. And by the way, if you ever join the Peace Corps, ask for Fiji. It's a pretty awesome Peace Corps spot. Yeah. Okay, so I thought I'd tell you first just a little bit about the program that funded the work that I'll be talking about. It's a statewide monitoring program. It came out of the debacle with MTBE, if anybody remembers that, where almost every gas station in the state leaked, and because there was an additive that was very soluble in water, the state kind of realized it didn't know which wells would be susceptible to contamination, and so that got the program started, and since then it's grown quite a bit, and of course I'm sure, as you're all aware, the last few years have just been incredible for groundwater and just moving kind of the understanding of groundwater in the state ahead, and so big changes, and that has led to the continuation of the program. Okay, and then I want to spend some time, especially with the first bullet there, tritium helium age dating. I was going to actually tell you in some detail how that method works, so that when you leave here, maybe that will be something that you can actually take away and remember. Okay, that's sort of how that type of groundwater age dating works, okay? And then the second part of the results will be about nitrate and figuring out the source of nitrate right in Chico. And yeah, so anyway, I'll show you applications from right around here and then a little bit wider around Chico. Okay. Okay, so yeah, here's a map of California, obviously, with the groundwater basins that are defined by the Department of Water Resources. There's something like 535 of them, okay? And so the high priority ones are in orange, and the lower priority ones, lower use ones, are in yellow. And then you have a bunch of wells, and these are Title 22 wells. So those are wells that are used for public drinking water, okay? There's about 16,000 of those in the state, and those, the ones that are outside of basins are shown with red dots, but obviously the, as you see there from the statistics over there, 95% of the public supply wells are actually in those orange areas, okay? So obviously the Central Valley is hugely important. The transverse and peninsula range, as it's called, the Los Angeles, Orange County, Salinas Valley, all the places that we think of as being heavily dependent on groundwater, okay? And this kind of categorization of the groundwater basins in the states has gotten more important as the statewide groundwater monitoring programs have come into being. So now we have CAS-GEM, which is really just groundwater elevation monitoring, but even that was a big deal to get that in the state. For a long time, there wasn't even a program, a statewide program, to monitor water elevation. Okay, so now we have that. They use a similar way of prioritizing where to get wells. And then now, of course, we have the Sustainable Groundwater Management Act of 2014, and that is going to prioritize areas that are being overdrafted, where sustainable use of groundwater is in question, where they're going to have to put a sustainability plan in place, also using a similar scheme to prioritize where to do that first. Okay, so That's a big part of the groundwater ambient monitoring and assessment program, which is funded out of the State Water Resources Control Board. Okay, it's a monitoring program that uses statistically distributed wells, measure a whole bunch of different things, some of which I'll tell you about today. Okay, and then in addition to that, there's a special studies program where we sort of zero in on certain areas and pick topics that have statewide relevance, but you need to look at them on a smaller scale. Okay, so these are just some examples of projects that we've done over the years. Up in the upper left, managed aquifer recharge, indirect potable reuse, where you're going to possibly use a wastewater source, and then that's going to reach a drinking water well. There's a lot of regulations about how long that water needs to be in the subsurface so that you have deactivation of bacteria and viruses. We actually put something in the water there. We put something in the water, and we watch it move to the wells, and see how long it takes, see what the dilution amount is to the wells. And so that was a study that we did at Alameda County Water District. That's one example of this type of project. Okay. We've done a lot of work on nitrate. Nitrate is the contaminant that is most frequently found in drinking water wells, and it causes the closure of a lot of drinking water wells in the state. Also, a lot of water districts are kind of very busy managing nitrate, so blending water sources or finding ways to keep wells going even though they might be above the MCL for nitrate, the maximum contaminant level, the regulatory limit. Okay, yeah, and then some more about managed aquifer recharge, and for instance, what kind of changes in the water chemistry happen when you take a water from somewhere else and put it into the ground, and whether you might mobilize some constituents that you don't want to mobilize. Overall, in general, you get an improvement in water quality when you put it into the ground, but once in a while you knock something off the sediments that you wouldn't want to, like arsenic, for instance. Okay, so yeah, so those are some examples, and then I'll show you, my examples that I'm going to show you here will be from the Chico area. Okay, yeah, so and this program uses non-regulatory approaches, so things that for instance, the Department of Public Health requires a lot from a drinking water well owner. They have to, quarterly, they have to send in, results of testing from many, many constituents. Volatile organic compounds and anions and all kinds of things, okay? We didn't want to duplicate that. Some of the constituents are the same that are required, but we would measure them at much, much lower levels than you would get from a commercial lab. In addition, we did things like groundwater age dating, because that tells you, allows you to understand where the contaminant might be coming from and just where recharge is taking place. I'll show you exactly how that works, okay? We look at water sources, the source of water. We move a lot of water around in this state, and so it can be sometimes interesting to figure out where that water originally came from, okay? And then we do look at some VOCs, volatile organic compounds, and emerging contaminants, things that aren't measured for regulatory purposes now, but maybe someday. So these are things like pharmaceuticals and personal care products, difficult to measure, generally found at very low concentrations, but can be interesting in terms of where did that water come from or where did that contamination come from, okay? And I'll show you an example of that in the Chico area as well. Okay, so age dating, the age dating part, okay, I'm going to spend a little bit of time on this. So if you think about what the age of groundwater is, of course, it's not the age of the water molecule itself, right? Water's part of the water cycle. You can do a weird calculation where if you pour a glass of water here, how many molecules of that water passed through the body of Isaac Newton or whatever, right? There's a few that did, okay? So yeah, so it's not the water itself. When you say groundwater age, it's the time since that water entered the saturated zone, okay? The time from recharge to wherever you're sampling it, to the discharge point, okay? And so, and if you think about a well drawing from an aquifer, it's not going to probably just draw one age of water, right? It's going to draw water with a distribution of ages, okay? So we apply a bunch of different isotopes to try to attack the different parts of the age distribution, okay? So some of them have a really short half-life. Those two at the top, sulfur 35 and sodium 22, those are actually kind of new to us. we're in the midst of developing those isotopes. You can see they have short half-lives. Sulfur-35 actually 68 days, okay? And sodium-22 is 2.6 years. You're talking about water, in the case of sulfur, is it this year's precipitation or last year's precipitation is basically the question that you can answer with the sulfur-35, okay? Sodium-22 has a nice half-life because you can see that that half-life isn't replicated on the chart among other ones. The problem with both of those, the difficulty in applying them is there's a lot of sulfur in the world and there's a lot of sodium in the world, right? And so getting the portion of the sodium or the sulfur that was produced in the atmosphere is the challenging part of applying those isotopes, okay? Then kind of color-coded in yellow there, I've got a group of isotopes that pretty much cover the same range. So there's sort of a rule of thumb with radiometric dating that you get about 6 times the half-life. Okay, about 6 times the half-life is the range that you're going to be able to date. So those particular krypton-85, tritium, helium, chlorofluorocarbons, and sulfur hexafluoride, they all cover a similar range. And it's sort of the industrial kind of modern time, especially in California, right? There wasn't that much going on in California like 80, 100 years ago, right? And so it covers this range back about 60 years or so in some cases, okay? And the tritium helium with a half-life of 12.43 years, that's the one I'm going to go into detail and tell you how that one works, okay? Then we have in purple there 2 isotopes, silicon-32 and argon-39, kind of the holy grail of isotope hydrology right now, okay? You can see that the half-life is different than the other groups. It's in a range where a lot of water that is used is in the range that you could date by those isotopes, okay? Both very, very difficult to analyze and to kind of figure out exactly the source of those isotopes, okay? So we are working with this group at Bern in Switzerland who's kind of ahead on the argon-39 and has showed some promise, okay? Then in orange, there's a group of isotopes with much longer half-lives. I mean, you get to go all the way up to iodine-129 with 15 million year half-life, okay? There you're talking really about sedimentary basin brines, right? That have been in the subsurface for a really long time, millions of years possibly, and tend to be salty water, tend not to be the water that we're drinking. Although interestingly, you know, if you go to places in North Africa, you know, they are using Pleistocene water, Pleistocene age water that can be dated with these isotopes, and they're using that unsustainably. Okay. Yeah, they have some issues with how they're analyzed and whatnot. Okay. Okay. So yeah, and keep in mind that it's the time since the water entered the saturated zone. Okay. And I just forgot to mention that many of these isotopes produced in the Earth's upper atmosphere, produced in the stratosphere, kind of come cascading down as cosmic rays interact with particles in the Earth's atmosphere, deposited either by wet deposition in rain or snow, or dry deposition in some cases, okay? A bunch of them are gases, see that? A bunch of them are gases that get dissolved in the water, okay? And so over the years, I've spent a lot of time, and we have worked pretty hard on dissolved gases in water, okay? And to me, it's like a little underutilized, frankly, considering how much information they provide about how water got into the ground and how fast it's moving below the ground. Okay, so they can tell you about what the temperature and pressure at the time of recharge was. Okay, they actually are an archive of that information. Once the gas dissolves in the water and enters the saturated zone, it's not going to interact with the atmosphere anymore. So it preserves that signal at the time of recharge. Okay, tell you a little bit about excess air, and then a bunch of the isotopes that are used for age dating are dissolved gases. Okay, and then you can also have interesting information about chemical transfer information. For instance, denitrification. So I'm going to talk about nitrate, and sometimes you get conditions where that nitrate is transformed to nitrogen gas, perfectly harmless nitrogen gas, and you can then measure that nitrogen gas in the groundwater and see, how much nitrate was denitrified. Okay, and then of course now we're getting more interested in looking for the possible effects of oil and gas production, including hydrofracking, and so you might want to look at things like methane, ethane. Okay, so now I'm going to move on to tritium helium age dating, okay? And so tritium is an isotope of hydrogen, okay? Hydrogen has 3 isotopes. The one that you think of as hydrogen is protium. Nobody calls it that, but it's protium. It just has 1 proton in the nucleus, okay? And then we got deuterium, sometimes called heavy hydrogen, got a mass of 2. About 1 in 10,000 water molecules in the environment is a deuterium isotope, okay? Then you got tritium, got 1 proton, 2 neutrons, mass of 3. Nature doesn't like that lopsidedness of the nucleus, and so it radioactively decays, okay? About 1 in 10 to the 17th water molecules will have a tritium as part of the water molecule, okay? And because it's radioactive, it decays to helium-3. That's where the dissolved gas part comes in, okay? So helium-3 is stable, okay? It's a beta decay. It's a pretty wimpy decay. You got to get a lot of tritium in some place for it to be a problem in terms of health effects, okay? So the source, okay, and so just like any kind of radiometric dating, right, you have when that water enters the groundwater, it's in equilibrium with the atmosphere, right in the beta zone, and then once it enters the saturated zone is when the clock starts ticking, okay? So you got a certain number of tritium atoms, right? As time goes by, 1 half-life goes by, half of those atoms are not going to be tritium anymore, they're going to be helium-3, right? After 2 half-lives, you got 1/4 of the parent and 3/4 of the daughter, and so on, okay? Just like any kind of radiometric dating, all right? And with any kind of radiometric dating, you have to know what you started with, okay? And sometimes that's not that easy. You know, with carbon-14, you got to look back at tree rings and find an independent way, basically, of figuring out how much carbon-14 was in the atmosphere at the time, okay? In the case of this method, one of the real strengths of this method is that we're always measuring both the parent and the daughter, okay? So the sum of those is what you started with, okay? We don't have to worry about what the initial value was at some certain time. We're going to measure the parent and the daughter, add those together, that is the initial value of the tritium, okay? Yeah, so this just kind of drive this home, okay? Is that at 0 years you got all tritium, and then at 12 years, you got a mixture of tritium and the daughter, helium-3, and at 24 years like that. And then this is just the age dating equation that is rearranged to solve for age and to have the ratio of the daughter and the parent in the equation. Okay. Okay, so, and tritium, as I mentioned, a lot of the isotopes that are used for groundwater age dating are cosmogenic, so produced in the stratosphere. Tritium is also produced cosmogenically. However, when humans figured out how to do nuclear fission, we added a lot of tritium to the atmosphere, overwhelmed really the natural production, okay? So this is called the bomb pulse, right? In 1963 was the peak of the bomb pulse, about September of 1963, okay? Then there was a test ban that both the US and Russia followed, and that, since then, really, the amount of tritium in the atmosphere has decreased both by decay and because the source is much, much lessened. Okay. So, and I just had a student who finished a master's thesis and really was working out here, trying to see, is there any bomb pulse left in surface water around California? And are we still above kind of the cosmogenic level or not? Okay. Yeah. So basically those sources of tritium get into the rainwater, then move through the vadose zone. Once it hits the saturated zone, that's when the clock starts ticking. Okay. In terms of age dating. So it's a dissolved gas in water, right? So you got to be really careful when you sample that. You can't expose it to the atmosphere. That would just tell you what's in the atmosphere now, right? We want to know what was transported into the groundwater. Okay. So basically, we pump this water out, and we pass it through the tubing into this copper tube, just like is on your refrigerator. Okay. And then clamp the ends of that copper tube and do a cold weld on that copper. And then you have water that wasn't exposed to the atmosphere. You can try to keep the pressure as high as you can, because if you let up on the pressure, then the gas is going to want to leave the water. Okay, so sometimes you get wet, but anyway, usually it's not too painful. So that's one of my graduate students collecting a sample at a monitoring well in Fremont. And then we're going to take those copper tubes that have the dissolved gas, about 10 milliliters only of the dissolved gas, and bring them back to the lab, okay? And hang them on this manifold, this vacuum manifold. Again, don't want to expose it to the atmosphere at all, okay? So you put this under high vacuum and hang those tubes up, okay? And put some dry ice down here, and then carefully uncrimp that copper and let the water drop into the dry ice and freeze it down like that, and then let the gas into the vacuum manifold. Okay. And yeah, so we can do about 10 samples at a time, 10 of these copper tubes, and it's totally automated. So luckily, all the valves are automated, and you can hang those things on there, make sure there's no leaks, and then tell the computer to go, and it goes overnight and runs the 10 samples. And okay, so that has all the dissolved gases in there, right? And most of that is going to be nitrogen, right? Just like the atmosphere, a lot of it is nitrogen. It's going to be some oxygen a lot of times in there, carbon dioxide, right? The ones we're interested in, the noble gases, are really, really low abundance, okay? So we got to get rid of those major gases, okay? So it seems like oxygen is super easy to get rid of, actually, because it's so reactive, right? So you just pass the oxygen by some charcoal. That's going to suck all the oxygen out of that gas that's moving through. Nitrogen's harder, it's not very reactive, but you expose it to hot titanium, and you can make a titanium nitride and get rid of the nitrogen that way. So the whole idea is take out all the gases. The noble gas is completely non-reactive, right? They're the only ones that are completely non-reactive, and that's what you have left, okay? And it's a very small amount of gas, but in a way that's a good thing, because if you know mass spectrometry, what gives you, real headaches in mass spectrometry are isobars, so things that land on the mass that you're interested in, right? If you take out all this stuff, you're going to have very, very few isobars, okay? So this is really one of the, so anyway, take all the reactive gases out, only let the noble gases in. Now we're going to separate those noble gases cryogenically, okay? So they freeze out at different temperatures. We got a refrigerator on there that goes to like 6 degrees Kelvin, okay? That's how low you got to go to get some of those gases out. But anyway, take them out one at a time, let them go through the mass spectrometer and measure them individually, including the ratio of helium-3 to helium-4, the thing that we're really interested in when it comes to tritium-helium age dating, okay? So yeah, so it's a sector field mass spectrometer, and in some ways it's the most sensitive type of mass spectrometry, and that's because of this thing where you're just measuring the noble gases, okay? So I know you're going to learn a new word here, okay? Yeah, so the detection limit for helium-3 is a zeptomole. Zepto, pico, femto, pico, femto, atto, yeah, zepto, 10 to the minus 21. 10 to the minus 21 moles. Yeah, so about 600 atoms is the detection limit of this type of mass spectrometry. All right, so I'm kind of acting like everything is all easy and fun, and there are times where that's true. However, the Earth generally doesn't cooperate that well, and so there are some complications, and there are some other sources of helium, okay? So obviously the atmosphere is one source of helium. There's going to be a certain amount of helium and the other noble gases in there just because of equilibrium solubility with the atmosphere, right? So if I had some water in here, there'd be a certain amount of noble gas in there that's just in equilibrium with the atmosphere, okay? That's the green bar shown here, okay? Then, interestingly, when water passes through the beta zone and into the capillary fringe and then into the saturated zone, it dissolves some gas bubbles right there, okay? And then when it gets into the saturated zone, the higher pressure makes those things dissolve into the water, okay? So almost all groundwater samples, almost all, are actually supersaturated. They're supersaturated with respect to the air, okay? So that's called excess air. It's called excess air because it basically has the composition of air, okay? And it does can tell you some interesting things, that how much of it is there, can tell you some interesting things about how the recharge took place, okay? So whether, for instance, there was a thick vadose zone or not. We can learn some things by looking at the excess air concentration, okay? And then the Earth's crust produces some helium isotopes by decay of uranium and thorium, and a little bit by lithium. On the helium-3, you can see that this is always a very small amount. This can be a large amount, okay, depending on the residence time in the crust. Okay, so a lot of uranium around, long time in the crust, you're going to get a big blue bar here, a big bunch of terogenic helium, okay? And then, in addition to that, when you get around volcanoes, sometimes around faults, you can actually have fluids that come all the way from the Earth's mantle. They're going to have primordial helium, okay, that basically messes us up. We don't like it because it messes us up for age dating, okay? So what we're really interested in is the tritiogenic, the part of the helium that came from tritium decay, okay? And that's this red bar in this example, okay? So you can see we're making a bunch of corrections, right? We're going to make a bunch of corrections to get this portion of the helium that we attribute to the decay of tritium, okay? And, but yeah, we learned some other things, and we always measure all of the gases, and we always measure the ratio of helium-3 to helium-4. Okay, so now let me show you some results and the kind of the power of the method, okay? Because, you know, if you want to know how fast groundwater is moving, what do people usually apply? What equation do you usually apply? Yeah, Darcy's law, right? And so you got to know the gradient, and what else do you have to know? Besides the hydraulic gradient, you have to know... Yeah, the hydraulic conductivity or the permeability, right? Right? Property of the material, property of the medium, right? How well do you usually know that hydraulic conductivity? Right? Several orders of magnitude. Yeah, you just don't know that thing, okay? So this is a completely independent way of getting this very important thing of how fast is the groundwater moving, where did it get in the ground, okay? So these are, okay, so here, in this example, this is down in Orange County, okay? So Disneyland is somewhere over here. Okay? And they do a lot of artificial recharge, right? In a way, it's amazing that they you know, provide water for the millions of people that they do down there. A lot of it is wastewater, and they push it into the ground at these different lakes that they took over quarries, right? And they load it up with hundreds of thousands of acre-feet of water, actually, every year. Okay. All right. So did 150 of these ages over this relatively small area, right? They have a lot of wells. That's the other cool thing about Orange County, right? So there's basically Swiss cheese of wells. So that allows you to do this kind of contouring of ages, right? Which you don't always get to do because you don't have the well density. But anyway, we did it here. And so what kind of things can you learn from this map? Well, one thing you can learn is where is the recharge taking place? The recharge is taking place close where there's young ages, right? So obviously around this lake, right? But look at this along the river here. You got a place here, definitely recharging, right? This place, not too far away, got pretty old water right next to the stream, right? So it shows you where the recharge is taking place. Not always an easy thing to figure out, okay? The other thing it can show you is, like, are there directions where the water's moving faster than other directions, right? So here you can see a place, right, this finger, where the water is moving much faster than, say, in this direction, right? So here, my guess, I actually don't know this, true or not, but, you know, Paleo Santa Ana Channel maybe, right? That is, it has some coarse-grained sediments here that's allowing that water to move faster that way, okay? And key thing, now we have a time. That's what the isotopes give you. There's an age, there's a time, and you have a distance. You get the velocity. You get the bulk velocity of the water, okay? So totally independent of Darcy's law, and we got a way to figure out how fast the water's moving, okay? And it's really a way to image the flow field, right? This is a shows you, you know, where the groundwater is moving and how fast, okay? Okay, so that's Orange County. The other thing I want to tell you about the noble gases, because it's a really rich data set, okay? So in addition to the groundwater age, we're measuring those other gases, and how much of the gas dissolves in the water is dictated by the pressure and the temperature at the time of recharge, okay? And the pressure is a function of the altitude, really, okay? The barometric pressure, okay? And then you can see that over this range that is pretty much the range that you're interested in groundwater studies, right? You get a pretty big change in the solubility, especially of the heavy gases, right? So these are the lighter ones, not much of a change, but when you get to the heavy gases, pretty big change in the solubility, okay? And we're measuring all of these things, so it's sort of an overdetermined system, but we do have two unknowns, the pressure and the temperature. But from this overdetermined system, we can get an estimate of the temperature at the time of recharge, okay? And the temperature at the time of recharge, not the same as the discharge temperature. So you're sitting there at the well, right, and you've got your little YSI meter, and you're measuring the discharge temperature and the conductivity and all those things, right? That discharge temperature actually doesn't tell you anything about where the water came from, but the recharge temperature can. It can tell you about how, especially if there's some topographic relief, how high up in the watershed that water entered the ground. Okay. So yeah, it tends to be interesting in areas where there's topography. Okay. All right, so these are the wells that, most of the wells in the studies that I'm going to tell you about are drinking water wells. So State Water Resources Control Board, that's sort of what they're concerned about. They tend to be good wells in that they produce well. You know, you don't have to worry about some wimpy little production rate, and they're clean, right? People are worried about the cleanliness right there, so that's good. Generally, you can get things like depth and screened interval and all those good things, okay? And it's something that we should be worried about, right? It's the water that people are using and drinking, okay? But the disadvantages are that because they tend to be open over a really long interval, you're going to get a big distribution of ages a lot of times, and everything is mixed, right? Everything is mixed. If not in the wellbore, then on the way there by dispersion, right? And so the signal that you're looking for a lot of times is really dilute, okay? They also, of course, alter the flow field. They themselves, right? The well itself is going to alter the flow field by forming a cone of depression. And, you know, because it's the water that people are drinking, there's some sensitivity. So I put that on both sides because people don't like to hear it that, you know, that there's a few parts per trillion of ethyl methyl death in their water, right? So, and then sometimes they say, we don't actually want you to come and sample our well. So that's not a good thing. That's when you send the graduate student. All right. Okay. So yeah. So the good thing about these groundwater ages are that they serve as a proxy for susceptibility. So if you think about it, water that got to the discharge point in a very short period of time, if there is a contaminant source in between, it's going to be pretty likely that it's going to be picked up there and at a pretty high and at a pretty not very dilute, right? So young ages, it kind of means it's susceptible to contamination, right? Didn't recharge from very far away. If there's any contamination in the intervening area, it's likely to be in the well, okay? When you get to really old ages, they tend to be, and this has come true over the years of looking at these data, tend to be completely free of contaminants, okay? So, I mean, anthropogenic contaminants, okay? They tend to, even when we look at really, really low levels, old water tends not to have any, okay? But the thing about old water is, if you're pumping really a lot of that old water, you're probably doing it unsustainably, right? It took a long time for that water to get there, okay? Sometimes thousands of years. Might have even happened in a climate and conditions that are pretty different from what you have in that area now, okay? So, in a way, we rarely give people good news, right? Tell them it's young water, tell them it's old water, probably unsustainable. That sweet 100-year-old water, lucky you get that, okay? But, yeah. All right. Okay, yeah, so that's basically how we use the groundwater ages. Okay, so I just wanted to also, just briefly, because I bet a lot of you are familiar with this, talk a little bit about stable isotopes, okay? So this is, the water molecule gives us a lot to work with in terms of isotope hydrology, because in addition to the hydrogen isotopes that I showed you, oxygen has 3 isotopes, so we use 2 of them mainly, 16 and 18. And when it evaporates from the ocean, just like you would think, the lighter one goes preferentially into the gas phase, and then when it condenses, the heavier one condenses out first, and the cloud gets lighter, and so on. Okay, and it's a temperature-dependent effect. Okay, more fractionation at lower temperature. And so, in California, we have a really nice physiographic gradient where we go all the way from a marine source of moisture to very, very high elevations. And so we get a big fractionation in a big contrast in the stable isotopes, okay? So the map kind of looks like this for North America, where, and people get weirded out by the nomenclature here, but everything is relative to seawater, which is defined as 0 per mil, okay? And then it gets more and more negative as you go to higher elevation and across the continent. And so you can see that in California, we have this really big contrast, right? Where we're going to have very negative numbers from higher elevations, values close to 0 at the coastal basins, okay? And wouldn't be as fun, right? Higher. Not much to work with there. Okay, yeah, so let me just then tell you that the other reason it's cool working with these in California is that we move the water a lot, right? We move the water long distances. In general, we're going to move it to colder, higher places, from colder, higher places to warmer, more coastal places, okay? And so when you measure the stable isotopes in a groundwater sample, it gives you an indication of where the precipitation source was, okay? Another way to kind of image the groundwater in the subsurface, okay, so now I'm going to show you results, okay? All right, so here's Chico here, okay? And then you can see some other wells. I might talk a little bit about, I'm going to talk a little bit about some of these monitoring wells later, okay? But obviously the concentration of wells that we had to work with in this study wasn't Chico. These are mainly California Water Service Company wells. Of course, Chico is dependent entirely on groundwater for the municipal supply, for the drinking water supply. And we got most of the drinking water wells in Chico. There's 72 or something in this data set. And Cal Water was very cooperative. And okay, so what you see here, every one of those dots is a drinking water well. Okay, in some cases it's monitoring wells, but I'll show you that in a minute. All right, but in Chico they're all drinking water wells. And so I had it color coded by the oxygen isotope ratios. Okay, and so what you can hopefully see here is that we have cooler colors, kind of in the center of this, and then going out in both directions, you get warmer colors, right? Heavier isotopes out in both directions, lighter isotopes toward the middle there, toward Big Chico Creek, okay? And so the way that we interpreted this is that in the outskirts, the outer parts of the basin, you're basically getting the local precipitation is what is providing recharge to those wells, okay? So -8.5, pretty darn good number for the rain that would fall in the Chico area, okay? As you get closer to the creek, you're getting a higher elevation signal, cold signal, okay? So this is water that fell up in the foothills, well up into the foothills, and is in the watershed of Big Chico Creek, right? So the water comes down Big Chico Creek, there's a big depression, groundwater depression in Chico because of pumping, and you can see how much of the water, you can see what fraction of the water is Big Chico Creek water versus local precipitation water, okay? So this was, we were kind of like really happy when we saw a pattern that was very clear that you could see recharge from Big Chico Creek, okay? And
that's oxygen isotopes.
That's oxygen isotopes. But you would see a very similar thing with deuterium. Okay, they basically behave in the same way. The reason that we usually look at oxygen instead of deuterium is you can measure oxygen a little bit more precisely. Okay, so you get a little bit smaller error bars with oxygen than with deuterium. Okay, so, but Chico is not special in this way up and down the Central Valley. So, so these are other gamma groundwater monitoring assessment program areas. So we got Sacramento there, and Lodi here, and some wells around Stockton and Manteca and Modesto, and see the same phenomenon, okay? So there you have even higher elevation headwaters, right? Because you're talking about the Sierra Nevada, you're talking about the American River coming down there in Sacramento, and the Tuolumne River, right, coming down in Modesto. And, as you move away here, you have Tuolumne River-like signature near the river, and moving out to a more local signature. Same thing in Sacramento. Okay, we have light isotopes near the river, heavier isotopes away from the river. I put the Chico ones on the same scale here so you can see how they look in comparison to these other areas. Okay, And, you know, Big Chico Creek doesn't have quite the same elevation contrast, right, as those Sierran rivers. But yeah, but it's a phenomenon that we observed all up and down the Central Valley, California. And, you know, I think in the natural system, you know, sometimes those rivers would be losing, but sometimes they'd be gaining, right? They're not gaining because there's a big depression in most of these towns, right? They're pumping the heck out of the aquifer, and it induces recharge. All right, so let's just look at tritium, okay? Tritium by itself. So tritium by itself, without the helium, it kind of gives you a yes or a no to the question, is there any modern water? Is there any water that recharged after about 1950 or not, okay? So the or not samples are the ones over here, all right? So these low to no tritium means basically all of that water recharged before 1950, okay? And we did find a good number of those in Chico and in some other places around in the northern Sac Valley, okay? So tend to be very clean water, high quality water. Gotta wonder about the sustainability of using that water that recharged that long ago, okay? And then there was another subset that, you know, falls in this range and really looks just like modern precipitation. And so plenty of modern water in there, okay? Interestingly, when you get out here, you're actually above the tritium concentration of modern precipitation, and you got some bomb pulse in the water. So remember that big peak in the tritium? Capture a little bit of water from 1965, and you're going to have a lot of tritium in the water. Okay, so that's what those higher tritium values are related to. Okay, yeah, and then one interesting thing about this study area, so this includes Chico and the surrounding areas, is that if the top perforation of in the well, so the top screen was 300 feet deep or more, then you really didn't see any tritium in the sample, okay? So that's the purple here. So you can see in the purple, you know, you got some that are low in tritium, even though they're screened, they have a shallowish screen, okay? So they have this range of tritium. But when you go below about 300 feet, you pretty much have almost no tritium, okay? So it kind of tells you like the depth to which that modern water has penetrated, okay? Now when you get, you know, so, and then the blue dots are the total well depth. And that just is telling you about mixing, right? So that's the total well depth. Might be really deep, right? The total well depth, but, you know, it might have some open interval that's quite shallow and allows some of that young water to get in there. So this kind of gets at this issue of the age distribution, right? So just because it's a deep well doesn't mean that it's going to pull old water. If it's screened over a big interval, it's going to maybe also pull some young water. Oh, okay, you know what? I'm going to totally hurry up here because I'm going way too slowly. Okay, so here's some interesting thing. One thing that was interesting about Chico, and we didn't really ever get to completely interpret because, anyway, so, you know, we got a bunch of good number of tritium dead wells. They kind of fell back here, you know, in this arc, back at the foothills. So this is the ages, you know, greater than 60 years, but the tritium showed the same thing, right? And, you know, if you think about, like, the water coming out of the foothills and, you know, maybe it's crossing some high permeability zones, right, some fracture zones and whatnot, you'd expect to see some young water there. But we didn't. We actually saw old water in the foothills. A little bit of a mystery, but tells you that really that water isn't getting into the ground up there and then making its way, you know, away from the stream. It's recharging from the stream down in town, you know, a little further downstream.
Could it just, you have many other dots of that same level, could that just be the background signal and you're not picking up the stream? Or is it really tied in physiographically to the foothills?
Yeah, good question. I mean, I'll get to these. These are some monitoring wells that have short screen and are really deep. So they don't have that same mixed effect there. Okay, I'm going to skip some things because, yeah, so let me just show you a little bit about the monitoring wells. So the ones with names there are nested monitoring wells, okay? So these are, you know, separate boreholes, but close together and screened over short intervals, okay, at different depths. And so, yeah, we sampled a bunch of those. I'm just going to show you like a schematic cross-section, okay, that has some of the data on it from that little thing. I projected them all onto this thing, okay? And yeah, so a couple interesting things here are that, you know, some of these have very little tritium, you know, well, below 300 feet, remember that, right? There's hardly any tritium. But even up here, not really very old. And you get this change in the stable isotope ratio, where basically you get lighter and lighter. So looking like, you know, a higher elevation recharge source. And we got a bunch of radiogenic helium, which means that it's been in the crust for a long time. And we got a low recharge temperature, low enough that it might even be Pleistocene water. Okay, so yeah, recharged at a time when the climate was pretty different. Okay, and we did it over here too and got similar results. So I won't show you that because I did want to get to the nitrate. Okay, yeah. Okay, all right. So yeah, and so nitrate, big problem all over the state. Big problem all over the state. You can see all the red wells are actually active drinking water wells that are pulling water that's over the regulatory limit for nitrate. So if they're using that well, they're having to blend that well and then show the state, the Department of Health Services that they're serving water that is below the regulatory limit for nitrate, okay? And then yellow, between 10 and 45, that's affected by non-natural nitrate for sure, okay? It's above any kind of level that you would consider the natural level of nitrate. So yeah, so big problem all over the state. The sources are things that often are co-located, so it's hard to sometimes pinpoint the source. They're non-point sources. They're important to the economy of the state. They're important in rural areas just for allowing people to live there, right? And, you know, why do we have that? It's because, you know, the use of nitrate from 1945 leveled off in 1990 or so, but still at this very high level, right, is just, yeah, very, very steep increase in the use of nitrogen. And, you know, if you really want to get all philosophical about it, you can't have 7 billion people on our planet without using a whole bunch of nitrogen. The way we do agriculture now, you've got to use a whole bunch of nitrogen or else you don't feed the people on this planet. So it's a huge problem, you know, if we're not going to completely change the way we do agriculture. Okay. So yeah. So anyway, Chico had a problem with nitrate, and so we came up and measured not the deep drinking water wells that I just showed you, but shallower monitoring wells. So the deep drinking water wells, there's very few actually in Chico that are affected by nitrate, but the shallow system, there's a lot of nitrate in the groundwater and a lot of wells that are over the maximum contaminant limit, okay? And the big question was, is it high-density septic systems or is it agricultural practices? And then when it comes to agricultural practices, are they ongoing or is that grandpa's nitrate, right? Grandpa applied the fertilizer, it got into the vadosome, it's slowly getting into the groundwater. Okay, so those were the kinds of questions that we were trying to answer, all right? Yeah, and so we can use the tritium helium goes over about the same time scale that the big increase in nitrate took place, okay? All right, so now the square wells are now in addition to the drinking water wells, and the square wells are where we did the nitrate study, okay? So we did the groundwater ages on those, and almost all of them less than 2 years old, okay? So we're talking about a shallow system here, rapid recharge. Yeah, still had the pattern though where you could see the big Chico Creek influence in the recharge, okay? And then a few that had a little bit older ages, okay? But much younger than the ages that we saw in the drinking water wells, okay? Okay, so how do we get at the source of nitrate, okay? So this is another little isotope tool that is used, and so this is nitrate NO3. Both nitrogen and oxygen have stable isotopes that you can work with here, okay? When nitrate passes through an animal, it's fractionated. You know, animals are actually really smart. Use that slightly lighter isotope. They use slightly less energy breaking that bond. The waste that comes out of the animal is heavier than what went in. Okay, so you get a fractionation there. Okay, so anyway, you know, if you look at a whole bunch of samples, this is kind of the canonical plot that's used to identify nitrate sources, okay? So the animal sources are pushed out this way in terms of the nitrate isotopes, okay? Because synthetic nitrate, they get the nitrogen from the atmosphere, you get these values that are high in the oxygen isotope of the nitrate, okay? All right, and then you can see that the boxes kind of overlap there, right? And this is actually a big challenge with working with nitrate isotopes, is that these boxes overlap. They overlap with the natural soil nitrogen, which is just nitrified out of the atmosphere. Plants, fix it out of the atmosphere. And so we often get a good number of samples, like we did in Chico, that fall in this range that overlaps, okay? And so you're sort of left with, what is the source of nitrate? Is it fertilizer? Is it just natural soil nitrogen? Or these, pushed out here, you could be pretty sure that they were some kind of manure or septic, okay? Okay, so because this happens a lot, that you get overlap, okay, we wanted to do something in addition to try to pinpoint the source of nitrate, okay? And if you think about those different sources of nitrate, what would come along with them as co-contaminants would be different things, right? So if it's a septic system, you might expect some of these personal care products or pharmaceuticals to come along with the nitrate, right? If it's agriculture, you might expect some pesticides, herbicides to come along, okay? So that's what we did. We measured a whole bunch of these things. This is like kind of analysis that I don't do. The organic people do it, and they're good at it, but it's not easy. You got to tell the instrument, I'm looking for exactly this compound. And yeah, anyway, it's complicated. But here's some that we found, okay? So we found herbicides or degradants of herbicides in a few samples. We found DEET, caffeine, surfactants from soaps. Carbamazepine is a anti-epileptic drug, okay, that is very, very commonly prescribed, okay? And so the kind of interesting thing is that, so in the square symbol is places where we saw one of these septic-related co-contaminants, okay? And the circle are places where we saw an ag-related co-contaminant, okay? And so, yeah, the squares tended to be kind of in town, right? And the circles tended to be on the outskirts, okay? And so the fact that we found some septic-related compounds was a pretty good indication that that nitrate came from septic systems. And Chico has, put in place a sewering, and that is probably well worth it and going to make a difference. Okay, I'm almost done. So, yeah, so, you could see, so just looking at the tritium helium age versus the nitrate concentration, you could see that the high nitrate samples were all in relatively young groundwater, right? When you got out here to the older ages, and the few samples that had older ages, there were generally low nitrate concentrations, suggesting that it's ongoing, right? It's happening recently. It's not a legacy problem, okay? Yeah. So sewering efforts are likely to pay off. All right, and I think I won't talk about denitrification because that would take too long. But there is some denitrification taking place in Chico. Yeah. Okay, so yeah, so river water is an important source of recharge. There's quite a few wells that produce completely pre-modern water, probably being pumped unsustainably. Okay, we actually saw some paleo water, some very old water in those monitoring wells in the deep part of the aquifer in the middle of the valley. And yeah, the shallow aquifer right in town affected by septic discharge and efforts to sewer it probably. Okay, thanks.